in the last few classes, we have been looking at the point group symmetries and also looking at how the point group symmetries can be combined with the 7 crystal systems. Because since we are going to deal with only crystals and crystalline lattices, we have introduced several grammar words as we went along. We introduced point group, we introduced space group, and we discussed 7 various crystal systems. We also introduced equivalent points, and then we introduced the number of molecules in the unit cell and so on. So, what I thought was, in the last 2 classes, even though you have got a reasonable gist of the whole thing, I thought I will make a set of slides which will completely revise what all we have studied, so that this is something which you will never forget. And in that sense, this class will be somewhat repetitive, but then it is constructive in the sense that we will now put all the knowledge which we have gained in order to understand how we take a crystal system, and in the crystal system we have a unit cell, and in a unit cell repeats itself to form a 3-dimensional crystal structure overall, and the points which repeat themselves in 3-dimensional space are referred to as the lattice and things like that. Okay. So, let us begin at the start with the least symmetric system, which is the triclinic system. In a triclinic system, there are no axes of rotation, and therefore, there are no planes across which reflections can take place. The only possibility that can happen in a case of a triclinic system is a point about which we can have the center of inversion. So, the possibility of having a center of inversion is the only issue which we have to consider in the case of a triclinic system. So, the 2 point groups which fall into this category are shown on the left. The one is the space group, the point group 1 with the equivalent point x, y and z, and the other is the point group 1 bar, which now takes any point x, y, z in space to any other point minus x, minus y, minus z. So, even though we have shown only one point here, this can represent a collection of points, and those points could be atom positions. They could be positions of ions. They could be positions of fragments of molecules. Whatever that is, they will always be following this particular point group principle. That is, in the case of the point group 1, there is only one set of such things, and in the case of 1 bar, we will have a the center of symmetry related equivalent point for every point. That means the center of inversion will be present on the set of objects which are represented by x, and the set of objects represented by the open circle here will represent that we do have a center of inversion. So, therefore, there will be 2 objects here, and that is why we say this system has 2 molecules or 2 units of repeat which are in the so called asymmetric unit of the unit cell. So, the unit cell of a triclinic system, as we have been defining again and again, is given by this rule: A not equal to B not equal to C, alpha, beta, gamma are not equal to each other. What we have to remember also, which we revised several times yesterday, is to remember that x, y, z are the fractions of A, B and C, and this is very important because the value of x, y and z is always in fraction numbers. So, suppose there is an atom here in a triclinic system sitting here, we will express it as fractions of A, fractions of B and fractions of C. So, if we say there is a atom at point 1, point 2, point 3, it means point 1 along the A direction, and point 2 along the B direction, and point 3 along the Z direction, considering the full length as 1, 1, 1 each. That means this 1 unit is taken as 1.0. So, the value of A will now appear at a distance of 1.0. Suppose there is an atom at the just about the end of A, then it is at 0.95, let us say. What it means is it is just away from the full length of A. So, these fractional coordinates therefore represent the positions of atoms or molecules or units or whatever. Now, what we also define is what we call as a lattice. In this particular case, the lattice is made up of points which are at these edges, the cell edges, and they will also repeat uniformly in all 3 directions, keeping the definition of a unit cell. So, in this case of triclinic system, we can have only one type of lattice where only the edges are occupied, and therefore, we call it a primitive lattice. So, if you count the number of lattice points in a primitive lattice, suppose you sit at this point and then count the number, there are 1, 2, 3, 4, 5, 6, 7 and 8 points. Now, each of these 8 points are occupied by 1/8 because the other unit cells surrounding that in 3 dimensions, they will also have this point as a common point, and therefore, each and every point here corresponds to 1/8. So, if we sum them up, 8 equivalent points, 1/8 occupancy of each, the total number comes out to be 1. Whenever the total number of lattice points is 1, we call such a lattice as a primitive lattice, and this is the primitive Bravais lattice. We have already seen there are 14 Bravais lattices with 7 crystal systems. So, this is the first of the case where we have a triclinic system with a Bravais lattice P. So, if we now combine the lattice with the point group symmetry, that defines what we call as a space group. So, the space group now represents the 3-dimensionality associated with our crystal. It will also tell us about the 3-dimensionality of the object that is inside this unit cell. So, whenever the objects are put inside the unit cell, their 3-dimensionality is expressed in terms of various values of x, y and z, and at the same time the lattice combined with the point group symmetry will define the so called space group. So, this particular space group comes up because of the definition of a group. For example, if you take 1 bar symmetry and combine it with the primitive lattice, it becomes P1 bar. Now, by the rules of the group definition, when we operate x, y, z, use the center of symmetry and take it over to x bar, y bar, z bar, we operate the center of symmetry. The inversion center takes x, y, z to x bar, y bar, z bar. The rules of the group say that once we have this coordinate system, if we operate on this coordinate system again the same operation, the same symmetry operation. So, x bar, y bar, z bar, in this case the same symmetry operation, we will come back to x, y, z. So, that way there is a closure property, we do not go out of this. When we have x, y, z, we get x bar, y bar, z bar, and when we have x bar, y bar, z bar, we get back to x, y, z, and we do not go out of the system, and therefore, this is known as a group. And so, such property is seen both with respect to a point here and with respect to the space, which is now made up of a lattice plus the point group symmetry combined, and which is referred to as the space group. So, the 2 space groups we can realize in a triclinic system are P1 and P1 bar. So, P1 gives rise to one such unit in the unit cell, and so we call it the asymmetric unit as well, and in this case z is equal to 1. We identify the number of molecules or number of units which occur in the inside the unit cell. Let us say number of molecules when we consider a molecular structure, then the number of molecules is 1. If the number of molecules is 2, it generally goes to a P1 bar position because it prefers to have a inversion center utility. But suppose we say that the number of molecules in the unit cell are 2 and it is P1, then it means that there are 2 different molecules, but not related by any symmetry. So, that means the presence of the so called XYZ in this particular case refers to what is known as a asymmetric unit. So, in an asymmetric unit there is no invocation of symmetry, whereas once we invoke the symmetry, it becomes now a equivalent point. X, y, z becomes minus x minus y minus z. These two are equivalent of each other from the symmetry operation, whereas x, y, z is by itself independent of it. So, therefore, that represents the asymmetric unit, that unit in which there is no symmetry operation, and then the symmetry operation when we operate, it becomes now the equivalent point in the space group P1 bar. So, this generally describes the overall view of any crystal system. So, when we talk about a crystal system, we talk about the crystal system, we talk about the point group symmetry associated with the crystal system and the corresponding space group that gets generated by combining the nature of this lattice, which is either primitive centered or body centered or face centered. In this particular case of a triclinic system, it is only primitive, and therefore, we have the point group symmetry, the space group information, the triclinic being the crystal system. So, whenever there is a material which crystallizes in this particular crystal system, all these issues which I have put on this slide should be identified and discussed. Once we discuss all these issues, then we say we have described the crystal structure. Now, the x, y, z can be more than one, as I mentioned. It could be x1, y1, z1, x2, y2, z2, each representing different atoms inside this unit cell. Now, if we find out the positions of x, y, z, that is the next step. In this particular step which we have discussed so far, we are not able to find out where x, y, z is. If x, y, z is at x, y, z, then all these rules apply. But where is x, y, z, we do not know. And that is what we want to eventually determine when we talk about the structure determination. We want to determine the structure of the molecule, where the atoms are sitting inside the molecule, and then we have to see how this molecule orients itself inside this unit cell, making use of the available symmetry information in the point group symmetry, and therefore generate the molecular dimensions in the space, in the three-dimensional space, which is allowed by the space group. So, again, to conclude this discussion on this slide, I will repeat. Crystal system triclinic, if we had to describe this in full, we have to first describe the unit cell, the nature of the unit cell, ABC not being equal, alpha, beta, gamma not being 90, and then we have to describe the corresponding point group into which the system goes into, and then talk about the equivalent points which we can generate, the presence of the symmetry element inside the unit cell. And as you know, once one bar is the point group symmetry, the entire three-dimensional aspects associated with the unit cell, every point in this unit cell will see the center of symmetry. And the centers of symmetry location is at this possibility as we have drawn, it could be at the possible edges of this three-dimensional box. So, the center of symmetry is here. The moment there is a center of symmetry here, one unit translation along A will create another center of symmetry, one unit translation along B will create another center of symmetry, one unit translation along C will create another center of symmetry. So, there will be 8 centers of symmetry that get created at all the edges. We have seen in the two-dimensional space group discussion, what we call as the plane groups, we have seen that whenever there is whenever there is a symmetry element at the origin and one unit translated, a same or a similar in many cases, but in this particular case the same symmetry develops halfway between the two. So, we will therefore have centers of symmetries at these positions as well, and that will tell us all the aspects that are associated with this space group. That point we will take up separately when we discuss the 230 space groups which form in the 7 crystal systems and the 32 point groups. At this moment, we consider only the space group and the corresponding point groups. So, we have 32 point groups, we consider only the crystal system, and when we want to look at the space groups and look at the details of the space groups, we will discuss them separately in a later class. So, this is the information I wanted to give you in a nutshell about the triclinic system. Let us see what happens when we go to the monoclinic system. When we go to the monoclinic system, if we look at the unit cell to start with, the unit cell will have this condition A not equal to B not equal to C, alpha gamma are 90 degrees and beta is non-90. So, one of the angles is non-90, and if beta is non-90, then it means that the twofold axis, which is a compulsory symmetry that has to be present to describe a monoclinic lattice, monoclinic cell, will have to be along the y direction. So, the y axis is the one which is then referred to as the unique axis. It is not necessary that we should always have the y axis as the twofold rotation axis, but convention says that it is better to keep it as the unique axis. There are cases where there are certain special properties seen on crystalline systems along other directions, and it so happens that it necessitates the definition of a twofold axis not being along y, but either x or z. In such a circumstance, the definition of the monoclinic cell will change. Instead of the beta non-90, we can have either the gamma 990, not 90, and this one alpha being not 90 degrees. So, one of the angles therefore is not 90 degrees, the other A, B, C are all independent of each other, there is no relationship between A, B and C. A is not equal to B and not equal to C. This brings up 3 point group symmetries, as we can see here. The first one is the so called twofold point group operation. The next one is the mirror operation, the so called M operation, and the third one is the 2 by M operation. As we see here that there is only one axis of symmetry. So we are now considering the case of one axis of symmetry being present, and therefore we have a twofold 2 bar which is M, and the operation of both 2 and mirror simultaneously. There is a twofold and there is a perpendicular mirror to the twofold axis. So these are the 3 point group symmetries we will consider, and the equivalent points you can write. In fact, we can see here the equivalent points are x, y, z and minus x, y, z bar. So you can write it down, x, y, z and x bar, y, z bar as the 2 equivalent positions. Similarly, in this particular case, you see that the mirror symmetry is notified like this. We have seen this convention. That means that the mirror is in the associated with the plane of our projection, and therefore you see both the points x as well as the other point which is generated by the mirror symmetry, which is an open circle. They will fall on top of each other. So in this case, considering B as the unique axis, it will be the equivalent points are x, y, z, x, y bar, z, x, y, z and x, y bar, z. It also amounts to an operation of a twofold symmetry followed by an inversion center. That is exactly what we have done here. We have taken the twofold symmetry and then we have operated the center of symmetry on that one. So suppose you take an object here which is x, you operate the twofold, you will go over there, and then you inverted it, then you come back here, and that is how we have an overlap of x and a open circle. Let me repeat, if you have this point, you operate the twofold, you go over there, but then you do not stop there, you invert it. When you invert it, you will come back here with the open circle, and that is what is shown here, and that is how you have a mirror symmetry invoked at this situation. In the last diagram which we have here, the third point group symmetry, which is the only other symmetry, point group symmetry which can exist with monoclinic systems, you see that we have 4 equivalent points, 2 corresponding to the twofold operation and 2 corresponding to the corresponding mirrors, because there is a mirror which is perpendicular now to the twofold axis. So we get 4 equivalent points, and you can write down as an exercise all the 4 equivalent points. Now we have the point group information on the left, we have the crystal system in the middle, and now we have to see what kind of a lattice this can generate. As you can see that we have a not equal to B not equal to C. So we have therefore 2 such situations. One is a situation where we can have this beta angle. This is the projection diagram of this, where we have projected the unit cell, and in this particular case this is the x direction. So this is the A cell dimension, and this is the C direction, which is the Z direction. So this is a AC projection, and in the AC projection you can get a primitive cell which corresponds to occupancies of the these are the lattice points, these are not atoms, these are lattice points. So the lattice points now add up. In this projection, if you take, it is a projection, so it is 1/4 times 4, which is equal to 1. So we will therefore have one total number of lattice points, and therefore it is a primitive lattice. So this is one possibility. The other possibility is because we have in the perpendicular direction a rectangular cell. We remember you did the plane lattices, and we found that there are 2 possible plane lattices, the primitive as well as the centered lattice, which we called as the little c. Now here also it is possible to have the lattice center at this point. That means you have now the lattice points at 0, 0, 0, this is 0, 0, 1, and this is the position at 1, 0, 0, 1 unit along x, 0, 0 along y and z, and this is the position where you have a value of 1 for x and value of 1 for z. This is the z direction, this is the x direction. So this will be 1, 0, 1. So if you consider these 4 now, defining these 4 points which are exactly the same, we will have the primitive lattice. But it is also possible to now have another set of 2 points as shown here, one in this line and one associated with that line. Essentially there is only one in fact, and that is removed by half along this direction. So, it is coming away from the like that, it is coming away from the origin, and at a distance of half we will have the presence of a lattice point. So, the lattice points therefore add up, this 4 will give us 1 and this will be half and half each, which will give us 1 more. So, the number of lattice points therefore is 2 in case of a C-centered lattice. So, these are the two possible types of lattices we can have in a monoclinic system, a primitive lattice and a C-centered lattice, and this gives rise to several possible space groups, and the possible space groups are also listed here for your convenience. So, these slides will be of immediate reference value as well. If you look at the previous slide, you have every information about triclinic systems, you have every information you want about the monoclinic systems on this slide. So, if you take for example the space groups to be primitive, the lattice to be primitive, combine it with the point group symmetry 2, you get P2, and you will get a space group Pm and P2 by m likewise. In all these cases, the number of molecules in the unit cell in general is Z equals 2, Z equals 2 in the case of Pm as well, and Z equals 4 as is illustrated here in the point group diagram. When we come to the case of a C centering, we can again have a C2, Cm and C2 by m. It so happens that when we have to generate the C centering lattice, what we have to do is to every x, y, z we add a half plus x and a half plus y, considering that it is C centered, that is the C direction is centered. If the A direction is centered, then you add half to y and also half to z. If C is centered, if B's direction is centered, then you add half to x and half to z. Let me repeat, you add half to x and half to z in case you have a C centered lattice, and in case of A centered lattice you leave out the A that is corresponding to the value of x and add half to y and half to z, and in case you have a B centered lattice, add a half to x and half to z, leave out B. So, this way you generate double the equivalent points. So, when we have a primitive cell, it doubles in the case of a C centered lattice. So, you therefore have 4, 4 and 8 respectively. I have given the example of C2, the equivalent points in C2 are x, y, z minus x, y minus z, because it is a two-fold operation. Now, these are the two operations which are generated by the point group symmetry. The lattice symmetry now generates two other points. So, this gives us half plus x, half plus y, z, and half minus x, half plus y minus z. So, you will have 4 equivalent points in case of the C centered lattice. What you have noticed also, as we have discussed this issue of equivalent points, is the fact that you are keeping the positions of x, y, z and the other equivalent points within the unit cell. In the way I have written here, for example, if you take x, y, z, you take x, y, z let us say at this point. Then if you operate a two-fold symmetry on this one, it will take you to minus of x, which is the other side of x, right, outside of the unit cell. Now, you will be wondering how you have 4 equivalent points in the unit cell. Let me demonstrate one example here, that is, you have now the two-fold, let us say this is the position of x, y, z. You operate the two-fold symmetry, the value takes it to minus of x and minus of z. So, the two-fold operation which is shown here, this will now correspond to x, y, z, and this will now correspond to minus x, y minus z. So, you take this point, keep it inside the unit cell, let us say we take the primitive cell to start with, we have this point and then the other point goes out of the unit cell. Now, here comes the information which we already have on the translational periodicity. This is the advantage in crystalline materials, and that is why we study crystalline materials. The advantage is the fact that if from here, if you add one translation along the z direction, you will come there, and add one more translation along the x direction, you will come there. So, you see that the equivalent points now are up here and up there, and they are related by a two-fold symmetry. Now therefore, there is a center of symmetry, two-fold symmetry created at the center. So that is how you get additional symmetry elements inside the lattice. So even though the lattice is primitive, the symmetry elements will insist on generating additional two-fold positions. The lattice is still z equals 1, but you generate these positions if you have a two-fold symmetry operation. In the case of the presence of the C centering lattice, you will have additional points. The same logic can be used by using translational periodicity associated with x and z and y. We can bring all the 4 points inside the unit cell. So if you have this point which is x, y, z, you will have the corresponding x bar, y, z bar up to here. So there will be a position which is now here, which is also a two-fold symmetry. Now because of the presence of the C centered lattice, we have to have, if there is an x, y, z, we will have a half plus x and a half plus y. So the presence of half plus x, half plus y and z will create a position up there corresponding to the value of z. Notice that minus x, y, minus z will take it there, whereas the half plus x then half plus z will take it to the position which is different. So we will have therefore 4 equivalent points after we do unit translations. So in order to see all the equivalent points inside the unit cell, you may have to perform translational periodicity included operations. So remember that, don't get vexed with the fact that once you operate the symmetry, it goes outside the unit cell. You can always bring the point inside the unit cell by translational operations, which are allowed only in crystalline materials, and that is why we study the structures in crystals, because we now have arrested these molecules inside the unit cell, which must obey the conditions we put on based on the space group and the crystal system. Right. The other aspect associated with this, of course, which we have not discussed fully, is the fact that we have these 3 space groups. Which of the space groups are centrosymmetric and which are non-centrosymmetric needs to be analyzed, and that is something which we will look again carefully, because P2 and Pm will generate equivalent points which are not involving minus x, minus y, minus z, and therefore they are non-centrosymmetric systems. And the x, y, z and x bar, y bar, z bar coordinates, whenever we get, that represents the centrosymmetric system. So the 3 point groups we have considered are 2 to m and 2 by m, and we have now discussed the possible space groups. So this has generated 6 space groups. Triclinic had 2. So we therefore have covered 6 plus 2, total 8 space groups out of the 230 possible space groups, considering all the 7 crystal systems, all the types of lattices and so on. It does not mean that as we go along we derive all the 230 space groups. That will take another 300 hours. That is not the idea. The idea is to give you the information on how these can be generated, and probably we go through each of the crystal systems, and once we reach a stage where we have understood the aspects associated with 1 or 2 crystal systems, the same logic will apply. So whatever logistics which we have to change from one crystal system to the other is the one we have to keep in mind. In monoclinic systems we have another possibility. That possibility that possibility is to use additional symmetry information. Okay. The additional symmetry information we have can come from screw axis and glide planes. We already mentioned about screw axis and glide planes. These are symmetry elements with translational periodicity. The screw axis is represented as 2, 1, and the glide plane is represented as A, C or N. We will discuss this independently and individually in the next coming slides.